Hello and welcome to the 2024 ELECOMP Capstone Design Program Virtual Summit. My name is Beckett, and today my partner Jaron and I will be talking to you about our project, which was sponsored by Hayward Industries, the VS-Omni diagnostic firmware. Our technical director for this project is Russell Buckley. He currently works as the test engineering manager at Hayward, and he holds both a bachelor's and an MBA from URI. As mentioned before, my name is Beckett Maestas, and I'm a computer engineering major. My partner, Jaron Gonzalez, is an electrical engineering major. And over the course of this year, we've learned a great deal about problem solving and our approach to engineering challenges. So we're excited to share the culmination of our work for you today. I'd like to start off by providing a little background information about Hayward for anyone who may not know. They're an international company that designs and manufactures high-quality pool products right here in Rhode Island. And they've been innovating in the pool sector for over 90 years, and in doing so, have become a trusted source for pool equipment. Now that we have some background information about Hayward, let's take a look at the product which we worked with on our project. This is the VS-Omni controller. It serves as a hub for controlling equipment ranging from filters and heating to lights and water features. Our motivation for this project is to help Hayward streamline the often costly and complicated troubleshooting and diagnostics process for devices which show anomalous behavior during use. Our goal was to provide a diagnostic firmware which could target each of the peripheral devices on the controller's PCBA to ensure the functionality across the entire device. Although we were unable to target every single peripheral device, we did significantly expand the testing methodology for this device by mixing firmware tests with external tests in conjunction with a bed of nails test fixture. On this slide, we can see the links we would need to go to in order to access the signals which were communicated along the VS-Omni's many buses. On this slide, you can see that we eliminated the need to solder the connections to the VS-Omni PCBA, which opens up a world of possibility for probing the system with scopes and logic analyzers to determine possible failures on the board. The main goal for this project was to enable quick troubleshooting and diagnostics so that the test engineering department at Hayward could work through the backload of defective devices in need of repair. As mentioned before, just troubleshooting these devices is both time-consuming and expensive. So in providing a system which could improve the process, we could also reduce overhead from component waste and troubleshooting time. Now that we're familiar with the goals of this project, I'd like to show some of the results we achieved. And on this slide, we can also see a basic system block diagram for this system. So we can see that we have our bed of nails, we have a series of modules which allow us to communicate with the VS-Omni in different ways, and those are all connected to a host which allows a technician or a test engineer to interact with the firmware. Since I have a background in programming, I primarily worked on implementing and testing the firmware. One of the biggest challenges I faced during this project was creating drivers for this system to enable communications between the Omni's microprocessor and peripheral devices. This was because we basically had to use macros and register definitions to implement serial communication drivers from the ground up. So this was fully embedded programming, there was no operating system or anything like that. And we felt that the resulting firmware was pretty nice. It could read and write a real-time clock module and verify the functionality of an external RAM chip. We also implemented a command protocol based on an existing Hayward protocol, which can verify that communications between the host and the VS-Omni have actually been properly transmitted. Another great thing about this is that it provides flexibility for use. So here to the right, we can see that the communication sent and received from a Windows application. But just as easily, we could use a Python script to communicate with the system running on something more lightweight like a Raspberry Pi. I also worked on testing the system. It wasn't enough for us to just verify that the firmware gave the correct user output. We had to make sure that with the oscilloscope that the data that was transmitted along a given bus matched what we intended. Finally, I also made sure to create documentation to show how future modules could be added to the firmware, how the firmware could be used with the test fixture, as well as how the test fixture itself could be used during the normal boot process to identify failures which the firmware could not target. With that, I'll hand it over to Jaron, who will give us some more insight into how the test fixture was designed and implemented.
Thank you, Beckett. For my individual technical contribution, I measured the PCBA board and pogo pins to determine best positioning and hole size for the test fixture. I created a layout for the test fixture using Altium Designer, created connectors for use with serial debugger in Raspberry Pi, and I assembled the test fixtures as we're going to see towards the end. For a layout of the PCBA board for the test fixture, I use Altium Design, as I said, and as you can see on the sides, there are headers that test engineers can use to test important testing points. I also added a reset button on the bottom, and so they don't have to unplug it and plug it back in. They just can hit the button and it will reset it. And on the top right, I also added an LED to indicate that the board is getting powered on. And on the top right, we also see the micro SD with the electro discharge protection. And every single pad that you see, a pogo pin is gonna be put in place, and that pogo pin is spring loaded, and it's gonna make electrical connection with the Hayward board. As you can see in this picture, this is how it looks when we got it. It's 50 pins, so that means 50 pogo pins, 50 testing points, and there are two boards, one stacked on each other to make sure the board is secure and the testing points don't move around, which can prevent maintaining electrical connections. Each pogo pin is spring loaded, and when the board from Hayward is put on top of it, you gotta apply pressure for every single testing point to make electrical connection. And we're gonna see towards the end how I managed to apply constant pressure for each pogo pin to make connections with our Hayward board. So for our micro SD with ESD protection, as you can see, our micro SD, as you can see, the diodes as close as possible I could get to the micro SD, because if you want to provide protection to a component, you wanna have transient voltage suppression diodes, or TV diodes for short, and that's gonna provide protection in case of electro discharge cases. For a USB to UART, since we have this right here, we can put it in. I added 4 headers, and you can just put it in, which makes it easy. And the headers like the TX and the RX matches with the microcontroller testing points. So for a test fixture frame, as you can see, these wing nuts, you screw it in, and that's gonna apply pressure. As you can see on the bottom picture of the wing nuts, there's 5 screws, and those screws at the tip, they have some sort of plastic to make it smooth. And when you tighten the wing nuts, it's gonna apply pressure, and that pressure is gonna make the pogo pins compress, and it's gonna ensure electrical connection. And as you can see in this picture, there's an LED, and here's our power being supported. And just for safety, because if you apply too much pressure, you can damage the board. So we added these nuts, and these nuts you don't have to move them around. That's like a safety. Like if you go past it, you applying too much pressure, and you can break the board, and that's just a safety measurement. And as you can see, to secure the 2 boards stacked together, I use these spacers to make them not move around and make it more precise, because every pogo pin, as you can see, has to hit the board, and if it doesn't, then electrical connection is lost. So on summary, our full AVO was not reached. We made documentations, shows how to effectively use the design to troubleshoot non-functional devices. A huge thank you to Russell Buckley, our technical director. Your dedication and knowledge has made this project possible, and of course, We would like to thank Dr. Harish Sunak. He is a ELECOMP Capstone Program Director. This is a rare, real world opportunity, and we feel thankful. Thank you.